Hey y'all, how's it going? This is your 4.3 linear functions note discussion. So if you could please make sure you have your notebook out, you're able to follow along with the video. Make sure that you're using the video to help you understand and also take your notes. So pause the video when you need. Sometimes I will instruct you to pause to do something. Other times when you need to pause so you can write something down or maybe rewind so you can listen to it again, please make sure you're doing so. So today we're going to talk about the definitions of linear versus function. Okay, so we were talking linear back more in chapter 3 when we were writing equations of lines, and in chapter 4 we're talking about functions, and now we have them paired together. So we just want to make sure that we're clear on the definition of linear and the definition of function. Then we're going to talk about looking at either a table or a graph and saying, is it a linear function? All right, so let's go ahead and dive into the conversation. So we're going to start with just a few definitions. So linear versus function, okay? So most recent, we've been talking here about functions in chapter 4, where we say that for every input, there is exactly one output. All right, so the different ways that we've been able to look at these functions, remember we had mapping diagrams and we had arrows coming across to be able to show those things, okay? So when we think function, we're thinking about using this tool, okay? We're looking at these arrows. Is there one arrow coming off of every input to show that there's only one output? We could be looking at a set of coordinate points and we could say, is this a function? And we'd say this one, no, it's not, because we're looking at these x values and there's a 2 here and a 2 here, and I have different outputs for them, okay? So like this is a function, this isn't a function. We should be able to look at a table, okay, and be able to do the same thing that we were doing with these ordered pairs. We visually are looking at the x's to see are there any repeats in terms of same input having two different outputs. So I look here and I say there's only one 1, only one 0, only one 2. So even if they had the same output, I don't care. I just want to make sure every input has exactly one output. So yes, that's a function. And then we've been able to look at graphs, right? And we've been able to look at graphs and we would say, okay, I have this graph here. If I do the vertical line test and I slice it along the graph right here at negative x equals negative 1, I actually have two coordinate points. I have -1, 1, and I have -1, -1. And that is not allowed because here I have -1, the same input with two different outputs. So I would say, nope, not a function. Okay, so again, the definition of function is simply asking about, does every single input have exactly one output? Okay, when we're asking the question about linear, we are basically asking visually, is it a straight line? Okay, in the simplest of terms, is it a straight line? Okay, and so a linear would mean that the graph of the relation, meaning set of ordered pairs, is a non-vertical straight line. Line implies straight, but I feel like when you put straight in front of it, it just kind of lands a little bit different, right? So is a non-vertical straight line. Let's see, a graph of the relation is a non-vertical straight line. And which means it has a constant rate of change. And this, guys, right here is the key for asking if something is linear. Because it's pretty easy when we're on a graph to be able to say, does the graph curve? I'd say, oh, no, that's not linear. It's curving, right? So I say, no, not linear. But whenever I'm given another graph and it's a straight line, I say, yes, it's linear. So that's kind of an easy thing here. But when we start looking at tables, okay, we start looking at coordinate points, we start looking at equations, this is what's most important. So rate of change is our slope. So we're trying to say that can the relationship between the information mean that everything changes at a constant slope? Because slope is a rate of, oh, that's not how you spell change, rate of change. Okay, so that's what I want you guys to start thinking about. When we ask the question, is it linear? We're asking, is there a constant rate of change, which makes it a straight line? If we get asked, is it a function? We're asking about inputs and outputs. Okay, so those are two different things. All right, so let's talk a little bit more about now we've combined them together, because here in 4.3 we're talking about, we're answering the question, is it linear and is it a function? Okay, so if I were to be able to look at this table, I want to show that I know how to go from a table to a graph, because I want to be able to use this graph to determine if this is a linear function. Okay, so let's see if we can go ahead and create some coordinate points. So right now I want to make sure that we are able to go from table to graph. All right, so my coordinate points would be 3, 28.5. That's this column right here, these right here, because I've got x, y. I would have 6, 54. I would have 9, 79.5. And I would have 12, 105. Okay, when I come to graph, let's review and make sure that we're graphing correctly. We want to make sure that we're labeling our axes, so x and y. X, if we look at the units, is tickets. So I'm going to write tickets over here. I look over at the y, and it says that it's cost in dollars. Okay, so I need to be able to plot these points. So the next step, before I even start plotting points, after putting the unit labels on the axes, would be to create a scale. So in order to choose what I should go by on the x, I'm going to say I need to get all the way from 3 to 12. So that's a range of 9. Let's see, do I have enough tick marks? 1, 2, 3, 4, 5, 6. Yep, I have enough here where I can simply just go by ones across the bottom. Because ideally, when we do good graphs, we're able to spread things out to fill the graph space. We don't want it to be all plotted in one little corner, and we also don't want to plot things where we have to be off the graph. So how do we create a scale where we can plot here in the graph space? Now I look at y and I say, what's my range? I got to get all the way up to 105. Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have 15 grid lines. So let's see, 105, I don't know what is exactly divided by that. I'm just going to go by 10. So I'm going to say 10, 20, 30, 40, and so on. So I have labeled my scale. So when someone looks at my graph, they know what they're looking at. Okay? Now it's time to plot. Okay, so I'm going to say 3, 2850. So I'm going to come over 3, and I'm going to go about where I think 2850 is. Okay? Then I'm going to do the next one. I come over 6, I go up 54, okay? Then I come over here, I go over 9, and I go up to 79.5, which is almost on the 80. Then I have 12, 105, so I go over 12. Ooh, how did I write this? I think this is my 12, okay? And then I go up to 105, and I plot that, okay? And so then I'm going to draw my line, make them a little bit bigger, through my points, okay? And so we would want to be able to answer the question, is this a linear function? Okay, so without even being able to give the specifics about where it crosses or maybe the slope, I would visually say that yes, it looks linear because it looks like when I go up, I go over by the same rate of change, which is making it a straight line. And when I ask the question, is it a function? I would say yes, 1, if I go up, it only crosses my graph 1 time. So if I did the vertical line test, for every input, there is exactly 1 output along the graph. So I'd say yes, visually looking at this graph, I would agree that yes, it is a linear function. Okay, so this is the example for graphing not only how to graph, but also being able to look at the graph and answer the question, is it a linear function? If you need to, go on ahead and pause. Make sure you've written things out. Maybe it took you a little bit to draw your graph because you didn't have grid paper in front of you. So make sure that you pause as you need to be able to fill out your notebook, okay? So let's move on and talk about how we would answer the question, is it a linear equation, or I'm sorry, a linear function based on tables, okay? So the first one was graphs, this one is tables. So this table right here is the same table we were just working with, and I'm gonna label this as, that is not how you spell movie, movie theater A, and this is movie theater B. So we are comparing prices. I've got tickets and cost of purchasing movie tickets, and we're gonna say that this is when we're purchasing them online. So if I go online to their site, I want to buy some movie tickets, this is helping me find out how much do they cost, okay? So let's go ahead and move this. I made it a little bit too close. I wanna be able to use that white space, okay? So now we want to be able to answer this question, is it a linear function? I don't have any graph paper here to be able to graph to try to figure it out, so I just simply want to use the table. So when we talk about being linear, we need to know, does it have a constant rate of change? So m equals change in y over change in x, right? So that's the rise over the run, okay? Which also means constant rate of change. We need to start getting really comfortable with all of these pieces looking like this and knowing that it all still means slope, okay? So when it comes to my table, to answer the question about linear, I need to know, does it have a constant rate of change? Is the change in y over the change of x the same as I go along? So if I start here on the table and I jump from 3 to 6, I added 3. When I jump from 6 to 9, I added 3. When I jump from 9 to 12, I added 3, okay? So I would say that my change in x was 3, and it was constant, right? Now let's check the y. So if I went from $28.50 to $54, I had to add $25.50. If I jumped again, if you do the math and you pause the video, you could always jump this on your own, okay? And then check and see if you get the right answer. But every time I jump, I am adding $25.50. So because when I jumped all the way down the table, you can't only jump once and answer the question. You jump every single time. And we see that the rate of change is the same. It's always 2550 over 3, 2550 over 3, 2550 over 3, okay? Which means that I can come over here and say that for this movie ticket theater, 25.5 divided by 3 is 850. And I would say, what does that actually mean? Okay, let's just go ahead and go into that because we want to make sure we understand units. That means that for $8.50, I can get one ticket. Okay, so if you see this change in y, cost goes on top. See this change in x, it goes on bottom. Ticket was the x unit. Okay, so we are matching units y over x. So because this had a constant rate of change, I say, yep, it's linear for movie A. And then when I answer the question, is it a function? I would say, well, let me go to every input value because this is the inputs and this is the outputs. I say 3 only comes to 2850, 6, 9, 12. There's no repeats. Okay, then that means yes, it is a linear function. Okay, now with this linear function, I could also write an equation y equals mx plus b using this information in the table. Okay, so we're not going to go there right now, but just know that if we say yes to linear function, then we should be able to do this. Okay, let's check movie theater B. Okay, so same thing, we're going to jump the table and we're going to say, what is the change in the x as I go along? Every time it's plus 3. Awesome. When I come here, in order to get from 27 to 54, I have added $24. To get from 51 to 72, I have added $21. I should already have some bells going off and say, well, wait, 21 is different than 24. I already know that this is definitely not linear. Because remember, jumping the table is answering the question, is it linear? Okay, so here I would say, well, my change of x was always 3. My change in y was different. So 24 divided by 3 is 8. 21 divided by 3 is 7. 24 divided by 3 is 8 again. And so I don't know. Like, there's nothing constant. I can't write a number down. So since I can't write a number down, and there is not a constant rate of change, that means that this is non-linear. Okay, so not a constant rate of change. Hard to talk and write at the same time. Okay, so means no, not a linear function, because in order to be a linear function, it has to satisfy both linear and function. So immediately, once it's not linear, we say no to nonlinear function. But let's just check. Is it a function? Yes, for every input, there's only one output. So even though it is a function, okay, we're not going to be able to write an equation that looks like y equals mx plus b, because it doesn't have a constant rate of change. So I'm not going to be able to do it, which means it is not a linear function. So when we're having tables, we want to be able to jump and check what is the rate of change every single time, and does it stay the same? Is it always $8.50 every single time we add tickets? Over here, yes, it was. Over here on Movie Theater B, we did not have the same rate of change. Okay? So I've already alluded to it, but let's make sure that we have it in our notes. So if you needed to pause and write down the information from our movie theater example, please do so. Otherwise, let's talk about when we say yes, it's a linear function. A relation can be represented by an equation in slope-intercept form, then it is a linear function. So we answer this question. If I can write y equals mx plus b, okay? If I can write the equation of a line, because we know how to do that, right? If I can write the equation of this line in this format, meaning I can go and pull the y-intercept off, plug it in for b, I can count my slope, and I can plug in my slope here for a constant rate of change, then yes, it is a linear function. If I am on a table, like we just did, and I am able to come up with the information, right, for a constant rate of change, and I'm jumping and I'm jumping, and I find out what m is, and then I go back and use my table in my Chapter 3 skills to find out what b is, then yes, I can write it in slope-intercept form. Yes, it is a linear function. Okay, so as soon as you answer the question, yes, linear function, I need you to start thinking, okay, how can I represent the relation, any set of ordered pairs, right, whether it's a table, a graph, you could even pull them off of a mapping diagram. If you said yes to linear function, you should be able to write y equals mx plus b with all of our knowledge about slope and y-intercept. Okay, so this concludes your 4.3 discussion. Make sure that you bring your questions to class, fill out your notes, and we'll see you in the next video.